Hello, my name is Kat and welcome to this video where we're going to talk about permutations with identical objects. I'm going to try and write better than this. Well, identical objects. Let's put a squiggly line under it. Why not? So, what we want to do first is make sure that we have done the prerequisite concepts and that we have them down well. So, let me go here to a question. We want to be able to do this 6.21 where we have different letters that we want to arrange, and there may be some restrictions or maybe no restriction whatsoever. So this video assumes that you're able to do all of this and we are ready to continue. So now let's see how my basic and factorial approach needs to be adjusted to handle letters that are identical. And what I want to do is look at this middle one, 6.3, that asks, how many different letter arrangements are there using the letters sassy? And now the S and this S and this S are all identical, so I cannot tell them apart. So that is the important thing, that regardless of how I write them, this S, this S, this S, and of course I have the Y, these S's are all identical. So if I ask you to turn around, okay, now turn around. Now I'm going to swap these S's. Now turn back. Do you see any difference in the arrangement? Not at all, because they were identical. So it's not quite the same as the previous one. Now what we're going to do here is figure out how to handle this. Once we figured it out, if you want to call it a formula to handle this, once we figured it out, it's as simple as just using it. We do not have to do this every single time. Please understand that. It's nice to know that you've seen it once, you do understand where it comes from, but like most formulas, there is a short, efficient way to do it, and we're not going to redo this every single time. But this video is trying to explain why the formula is what it is. Why do we do it the way we do it? So, first we can't answer the question of arranging this. First, we're going to ask, my writing today is not very good. Feel free to comment about that in the video if you feel like it. But I'm doing my best. First, we're going to ask, let's make them different. Make the letters different. Whoa, that was supposed to be a D. Make the letters different, and then let's arrange them. Well, we know how to do that, so let's make them S1. A, nothing else looks like the A, so we're good on that. And let's call this guy S2, S3, and of course Y is pretty unique as well. We can arrange that. That's going to be the number of ways to arrange different objects. There are 5 of them, 5 factorial. And we know that comes out to 120, whether you do 5 times 4 times 3 times 1, 2 times 1, or you do it on your calculator. Either way, it is 120. So now let's look at some of these. Let's look at some of these arrangements. Of course, 120 is a whole bunch. And I don't want to write them all out. Let's just look at some of them. I'm going to have what I'll call my template. And some of them will follow this template, some of them will not. Let's pick a template where there's an S at the start, an A maybe, and then a Y, and then an S and another S. Says. Now, which ones look like this? The actual ones have numbers, so it could be S1, A, Y, S2, S3, or S1, A, Y, S3, S2. These are now different, remember, because we numbered them. So if I swap these around, they're different among this 120 arrangements. I'm not asking the question in the PDF. I'm asking a question I can handle. And now I'm looking at the answer I get. Another one arrangement that fits this template is S2 maybe first. AY, S1, S3. S2 can be first, AY, S3, S1. All of these are different in the 120, but they all follow this template. And of course I can start with S3. AY, S1, S2. S3, AY, S2, S1. So what I've ended up with is a grouping of 6 labeled arrangements. The S's are labeled, but they all sort of follow the same template. Let's find another template. There are, of course, many. Another template could be, say, where all 3 S's are at the start and then the A and the Y. But because they're all labeled, the 120 will contain a couple of different ones. It could be S1, S2, S3, AY. S1, S3, S2, AY. Those are different. S2, S1, S3, AY. S2, S3, S1, AY. And hopefully you see how we're making these. We're just shuffling the S's, which are now different in all possible ways in their position, which under this template is the first 3. S2, S1, AY. So again, we get a grouping of 6. Now, let's think about this for just a second as I check how much space I have. Ooh, I have lots of space. Yay! How do I relate this 120 to my actual question? So the actual question was really the same as how many of these templates are there? Because here, the S's don't have any labels. These are really the ones I'm looking for. These are the ones I'm looking for. So the actual question, which we can say the number of, I'll call them unlabeled arrangements. Just so we can remember, this is the one that the question actually wants. The original sassy. The S's don't have any labels. That number is the same as the number of templates that we can make. I just gave it a different name. Same thing, really. Because in these templates, we say where the S's go, we don't actually label them and say which one. Inside the grouping, we say which one. So the number of templates is the same as the number of groups that we made among the 120. Now, why is the group size 6? Well, For now it is 6. Maybe you see, maybe you don't. I don't need to know. I am looking for the number of groups. Now think about it this way. There are 120 of these labeled arrangements. They come in groups of 6. How many groups are there? Well, that is the basic concept of division. It's 120 divided by 6. If I say, for example, I have lots of people and they all wear different shirts, and some people are wearing yellow shirts, and some people are wearing orange shirts, and some people are wearing blue shirts, and all the colors come in groups of 6. How many different color shirts are there? That is the basic concept of division. So I can find my answer very easily as 20. Therefore, there are 20 ways to arrange the letters in Sassy where the S's are identical. Identical. Now, that's great for this question, but it doesn't help me find a formula. Oh, but it does. Because this 120 came from the 5 factorial, which was where I temporarily didn't look at what they were. I just arranged them as if they were different. 5 factorial. This 6, however, comes from what? What did we really do to get the 6? Instead of making a list, we could have found the 6 without making a list, just by understanding what options we have inside this template. The only options are shuffling the S's around in those positions. There are 3 labeled S's inside this group. They can only be, in this example, first and the 2 last positions. In how many ways can I shuffle 3 things around? 3 factorial. And that is why it's 6. 3 factorial. It's because I'm shuffling 3 S's. And there is the formula that I'm interested in. So now what I usually tell people is, you don't have to write the formula in a specific way. I'll do something here, but write it in a way that makes sense to you. It doesn't matter how sloppy it is. It doesn't matter how messy and confusing it is to someone else. What matters is that it makes sense to you. No one else. So, the number of ways to arrange objects where some of them are identical. Again, don't follow mine. It's going to work for me. Other words could work for you. As long as you understand how to apply this. So I'm going to make a line. I'm going to try and make it straight. And it's going to be long because I'm using words. It's the total number of objects, regardless of what they look like, factorial. We had 5 objects. I don't care what they look like. It was 5 factorial at the top. Yeah, if you want to know why, yes, we explained it, but I'm not doing that every time. That's silly. It's inefficient. Underneath is the number of identical objects, we can say, factorial. Now understand what this means. there are 3 identical S's, therefore it's 3 factorial. Alright? Now, how does this extend? You can ask, well, what if we have other letters here? What if I temporarily, I'm going to go, where's my eraser? Erasing time. Let's, for example, back to the pen. Where's my pen? Pen. Come here, pen. There we go. Let's, for example, assume the question said, these were the letters. Sassy. 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 What would really change? Well, then I would have an A1 and an A2 to make sure everything's different. And not only in here do the S's shuffle around within a template, but 2 A's would shuffle around as well. So the group would then change to arranging 3 S's, but also arranging 2 A's. And the total would, of course, change to a 6 factorial, yes, because there are no total of 6. And the group size would change as well, depending on the options I have to shuffle similar type letters around. So this would then be 6 factorial over 3 factorial times 2 factorial. So over here, each one of these, for each type of identical object, not necessarily letters, usually we stick to letters, I do this at the bottom. I add one of these, I include one of these factorial numbers at the bottom. Okay, let's make a new page. I should have done this in advance. I'm just not very well prepared here. And let's look at the next example, where we want to arrange the letters in intelligence. Intelligence. So now you look, first of all, there are duplicate letters. So my formula is going to say, I'll do it like this, over here. So this is now exercise 6.4. The number of ways to arrange this is going to be, remember we have the I here. How many letters are there? I, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 in total. Now which ones are identical? We have 2 I's. We have 2 N's. 2 N's. We have T is unique. 1, 2, 3 E's. 3 E's. We have 2 L's. And I think that's it. The N's are covered. G doesn't look like anything. Okay. So that means underneath the line, 2 factorial times 2 factorial times 3 factorial times 2 factorial. All of them for each group of identical letters. So that is the main concept of why, zoom out, of why the formula is what it is. But once you have it, you can just use it. You don't have to do the whole thing again. Okay, that's the important thing. You don't have to do the whole thing again. Oh, you want to just zoom out there like this? There we go. Okay. Now we can do other examples and look at letters like A, B, C, D, E, 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 and arrange them. First under no restriction, and then in a similar way as before, we can glue stuff together and do all kinds of things. So let's do it. Why not? So first up, we have this exercise, 6.5. And our letters are A, B, C, D, E, E, E. And of course, as you can see on the printed page, the E's are identical. Okay? Regardless of how we write them, they are identical. So first up is no restriction. Let me zoom in here. We can do them side by side. Now I was zoomed out, so this is why these look really bad. So let's just cover that up. First one, no restriction. The number of ways. I'm going to look at my ugly letters. Don't look directly at them, just sort of on the side here. How many do I have? I have 7. Which ones are identical? The 3 E's are identical. That's all you need to do. If someone asks, well, why on earth do you divide? You can then go and say, oh, here is a more detailed explanation about the logic for where this comes from, blah, blah, blah. Do I want to do that every time? No, of course not. That's ridiculous. Now I have to go and look what was my other restriction. Oh, I'm hiding behind it. Ha ha ha. Oops. Second one is the word bed appears. Maybe you're sleepy. Bed has to always appear. Alright, let's do it. So what are my steps for keeping things together? Oops, there was supposed to be a 1, not an S. Glue. What am I gonna glue? I'm gonna glue B, E, and D all together and arrange. I also still have A, not B. I do have a C still, not D. And I do have 2 E's because I only glued 1 E. Does it matter which E I glued? No, because I can't tell them apart. So, I have 1, 2, 3, 4, 5 things. 5 factorial. But 2 E's are still identical. Now, when I glue, there's always a second step. I unglue the B, the E, and the D, and I arrange inside that super letter. Sorry, I'll try to write a little better. I'm just so excited, so I go. Whoops. Sorry. Got carried away. But when I unglue, what options do I have to arrange the letters inside? 1. Because it has to be the word bed. So then the total number of ways to complete this experiment to end up with a valid arrangement, blah, 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 is whatever came from step 1 times whatever came from step 2. And I write the 1 to emphasize that I've done both steps, to remind myself there is always a step 2. Next, let's see here. I don't have a... If I go out... there it is. Nice. Hold on, I think I'm going to cough. You don't want to hear that. I'm back. Now, the A and the B appear next to each other. So very similar than before, but with this new collection of letters. The A and the B next to each other. The A and the B next to each other. Alright? So, I want to keep things together. Step 1 is glue them. See, that was supposed to be a U, and I just merged it with the E. What do I glue? I glue A and then B. That's my choice. What is happening? I cannot write an and symbol. And then I arrange the A and the B. Seriously, stop it. With, I already have an A, I already have a B, so C, D, E, E, E. How many ways can I do that? 1, 2, 3, 4, 5, 6. 6 factorial, but 3 E's are identical, and therefore I divide. I hope you're getting the hang of this slowly. I have a gluing step, therefore I have an ungluing step. Unglue. What do I unglue? The A and the B, because that's what I glued. And then I arrange only inside. Only inside. If you want to see a video on exactly how this process works, in a little more detail, without the duplicated letters or anything, let me know. Then, the number of ways just to complete step 2 is, well, I do have options. It could be A, B, or BA. So, the number of ways to arrange the A and B while still having satisfied the restriction is 2 factorial. Then, by the way of the basic principle of counting, says take the number of ways for step 1 and multiply it by the number of ways for step 2 because it was one followed by the next, which is multiplication. Now we just need to make a new page here. New page there. And then we can do the last 2. Number 4, all the E's appear next to each other. All the E's appear next to each other. So let's do it. Big screen. Zoom, zoom. Zoom, zoom. Oh, there's the top of my page. There it is. Alright. So this is number 4. All the E's next to each other. So I still want to keep things together. Glue them. What do I glue? E. One super E. And then I arrange that with A, B, C, and D. So I have a total of 1, 2, 3, 4, 5 objects. Are any of them identical? Well, this super E doesn't look like anything else. These are all different. That is it. But I did glue, so I should consider the next step, which is ungluing. What do I unglue? And yes, unglue is a word. We've decided it is. I unglue my super E, and I check if I can arrange inside it while still making the restriction, the question, happy. Can I? Well, technically, yes. There are 3 things, and I need to shuffle them, but they're all identical. So you could say here that, which does follow the formula, or it simplifies to a 1. But I kind of like this one, because it shows that the formula still covers even the case where everything is identical. So my total number of ways to do this is whatever came from step 1 times whatever came from step 2. In this in this conclusion, I don't rethink what I did here. I found the answers for each one. I'm putting them together, whatever they are. My thinking is done. There was one more. What was it? Where's my button? There we go. B and D do not appear next to each other. I don't want them next to each other. Alright? Well, I know from experience it's always easier to keep things together than it is to keep them apart. So what I'm going to do is make a plan. What I want is B and D not together. How I'm going to do that is instead take absolutely everything with no restriction and take away the opposite, the complement. Complement. What is the opposite of B and D not together? Well, B and D together. And I know that's much easier. So the number, oops, that was supposed to be a number of ways, no restriction, but we can go all the way back to that ugly, ugly letters. Ew, again, look at them. And the total number of ways without any restriction was 7 factorial over 3 factorial. Then, oops, factorial. The B and the D together is the same as the A and the B together. 2 letters. The same strategy applies. And it was this one. 6 factorial over 3 factorial times 2 factorial. The same thing applies. And there you go. The indirect approach wins the day yet again. I should always think, what's easier? To count what they want directly, or to count the opposite and just take it away from the no restriction total? In this case, almost all cases, keeping things together is much easier than directly counting, keeping them apart. Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Also, please visit me on my Patreon page if you want to support me in making further content. Thank you.